Okay, so firstly, thanks everybody for coming. Also, thanks Leonardo's your introduction. So also thanks the invitation of the ARC Data Center. So yeah, it's my delight today to give a speech about my research in large language model for material discoveries. Yeah, as mentioned before, so we are believe that generative AI and also material large language model will bring a new paradigm in material discovery in the future. Um, there are some very well known or some Nature publication, journal publication recently about using the AI, also generative AI to for my discovery. So one is from the left one is from CMU and another right one is from Berkeley. So the autonomous lab with the chemical with the autonomous lab with the AI now can find a new material for us. So as reported in the Nature publications, so they found 41 new materials in only 17 days. So usually like we need to find a new material, like is one material need 2 to 3 years. So you could see that AI now, how fast this AI now can discover new material. So the opportunities, so why we need also the history of the material development, so shows that the AI, how we transfer the paradigm, like and also our future. So at maybe 2,000 years ago, so we find a new material only for survive. So the purpose of the new material is for survive. So at that time, our human know how to use stone, wood, animal, plant. So it's totally from nature and no processing. So we just find something and we use that and do some very little bit engineering. And then then we move as time goes by, we know more more processing and we know some for example, we selection of the material based on experiencing it with some more complex processing. So we know how to use iron, copper, and wood processing. So there's some experiment, but it's not like modern science experiment. And after the maybe 200 years ago, so the first revolution of the engineer of the industry. So we know how to use alloy polymer. So this is the modern like physics, chemistry, material science coming out. So we know it's still like a selection of the material based on experiments, but with more complicated process. And we can create alloy polymers and we do processing improvement, structure component analysis, and also we synthesize a lot of new material and we find a lot of new elements in the last 200 years. Actually, we're still at this stage, but with 200 years history of our material science, we have a lot of data, we have a lot of experience, but we don't have the efficient way, efficient framework, efficient tool to help us to analysis, to help us to break the limit, push the boundary of the material. So that's the reason why we need AI. So we need an intelligent material, we need a more sustainable development, and we need intelligent manufacture. And now material design also consider far more things than ever before. So for example, the phone that you used 20 years ago, maybe 5 years ago, is totally different compared to the phone that you use now, right? So there's more material inside. And therefore you need to consider more parameters when you design a new material. So for that reason, so we want to shift the Eureka-based material discovery. So so material discovery now is like a lucky. So sometimes in my lab I find something, but if I'm not lucky, so maybe I cannot find the material in 5 years. That's possible. So we want to make that Eureka-based moment to AI-driven discovery. We want to discover more materials and more bring us more new interesting products to change our human life. So for that reason, so we create a USW Air for Science group. So we focus on NLP, CV, and also traditional machine learning to actual material design. We want to predict the material and also want to accumulate all the scientific knowledge existed in the paper to help us to discover new material. Why we need AI? So so the problem is that the material designs have massive candidates. So if a material contains just 20 atoms, there are as many as 10 to the 25 all possible structures. So there are so many possibilities in the material, and also have so many elements that could be used. So even there are not all the elements that we could use, but still there are a lot of possibilities. It's infinity. So if we want to use AI, so we need to data. So right. So I think some of you guys are very familiar with machine learning, deep learning, all these things. But these things like apply to our daily life. For example, computer vision, we use a lot of data. We use a lot of pictures. For example, training OpenAI GPT models, they use a lot of data, online data on the website. But the data for science is very expensive and few. So if we need to train a data, we train a scientific model. We need some for example, we need a lot of paper. We need some simulation data, or we need some experiment data. So this is the crystal structure of a material. So these data are very expensive. So even the most cheap one is simulation data, but simulation in material is also very expensive. We need supercomputer to simulate all the possibilities, and also there are very less data. They are very sparse. So we need some new techniques, new models to different from the traditional normally used the deep learning model framework to train the AI model for material discovery. So here also, so experimental and simulation data both are very, very expensive. So machine learning, so there's an example how machine learning used in material science. So for example, here is the material structure. So each one is a new material, and we will convert. So what we will do is that we will convert the material with their important parameters to convert to descriptors, and we accumulate a lot of data. Normally, it's from simulation data, so we don't have so many experimental data to train the machine learning model. And we train the model based on this data, based on the descriptors and the label. We found a relationship between them in the machine learning model in black box. Yeah. And then if a new material come in, so then we will convert that material structure to a new descriptor. So it's kind of like a dictionary translate to matrix. And then with that model we trained before, we will predict the label. The label is the property that we want to predict. Yeah, they are very successful, but the only suitable for the first thing, you only suitable for tabular data. So for example, you should like a data like Excel, but normally that our data is not Excel because we are experimental scientists. So material is a subject highly related to rely on the experiment. So experimental scientists will not create a data, create Excel sheet like that. Also, design the material descriptor is also very time consuming because you cannot use all the parameters in the to convert to descriptors. So for each prediction of the properties, you need to design a new model. So when you design a new model, which means that it's still very expensive, and you need a lot of specialists to do that. But it works for some very popular properties. For example, bandgap is a very popular property, used in all material subfield. So bandgap is very successful, but there's still a lot of things not solved by machine learning previously. So actually, as I mentioned before, the most of our data in the material science is and also chemistry are mainly unstructured data. So for example, like journal, paper, lab report, and it's like that. But we lack of the method to processing them. So there are a lot of data existed. There's a gold, but we don't know how to mine it. For that, so that is my research. So my research mainly so this is a research we did. We have a trial have a taste 3 years ago. So we want to do a prediction with a latent knowledge in the water embedding. So what do we use? That is so every day you open your keyboard, so you add something so here is the example. I want to eat the beef. So it gives some recommendation of the the things that I want to input. For example, like a beef stick or emoji. So why my iPhone know I want to input that? Because they learn my typing habits and also maybe other people's, maybe you guys typing habits and give me the recommendation. So this how they do that recommendation is very famous algorithm 10 years ago published by Google. So it's the word to vector, word to they convert each word to a vector. So we call it word embedding. So for example, I know man is a king, king is a man. So then I can let the computer predict that the woman is the queen is a woman. So why do we know that? Because they convert all the words to a vector, and then in the vector space, they can calculate the distance and angle between the man and the king vector. And then because man is very similar, king is very similar to queen, so they find a similar angle between the distance between the man and the king, so they can predict the queen is a woman. So we applied that method to the literature, and we want to whether we can find some new material based on the literature word embedding. So we want to find a brand new like electron transport hole layer or hole transport layer, and this is the is like a figure to show that relationship. So for example, zinc oxide and is a electron, so it's a transparent conductive layer, and titanium oxide is a electron selective layer, and nickel oxide is a hole selective layer. So we found a similar angle, and we found some new material based on the angle distance on the existing findings. So existing, we know that zinc oxide is a titanium oxide is a electron select transport layer. So whether we can, based on that relationship, and we can find some new material that could be used for electron transport layer, which we didn't discover before. So we truly find some new material, and we do experimenting, and we found that it's very interesting. The performance is pretty good. So, yeah. So this is one example. Another example is that this is the paper that I worked with Clara 2 years ago. So we apply sentiment analysis to help us to evaluate to find a new material synthesis method. So sentiment analysis is very which also be called opinion modeling. So it's kind of like a so for example like when you buy something on Amazon, so you will give comments on that product. So it could be like a positive, it could be negative. So we'll apply that to the literature. So here's the example of the opinion in the product review. So excellent product at great price. So towards a laptop on the Amazon reviewed by who in the United States on what time. And this is the example that we define in the scientific literature. Still, thesis and application of the Reunion thin film has been limited. So thin film and application is the expert, and the Reunion thin film is the name, is the material. It's similar like a laptop. And limited is the sentiment. So this is negative. It means that it's not been explored yet. It has some obstacles to solve, and by who, and also time. So we created like around 70K paper about the nanomaterial synthesis method, and we do a recommendation based on we extract the opinion sentiment out of the material and their synthesis method and also the application and we predict in the next 5 years like the top 10 material oxide material that could be synthesized by the atomic layer deposition. So LLD is a new synthesis method that is a new synthesis method that not all the material has been used before, but there are some material because it's very expensive so we didn't recommend all the material use that method to do thesis. So we recommend 7, and when we do the with our people under review, the lithium forest like material oxide has been successfully synthesized in Norway, so which never been synthesized before. So that is a very interesting result. So with the entropy, so natural language processing, and so in computer science, applying to material science, which we could find some new things that we never find some like help us to predict the future like that. Yeah. So why do we need a large language model? So we need language model. So because data, so our material science data is usually depends on its context. So for example, like information such as material, manufacture data, synthesis data is very, very complex for data in the tabular format. So for example, here I give an example of the material synthesis method. So you can see that some people, so for one material that it could be synthesized in 2 step or in 3 step or like some sub steps. So it's very hard to if you use a table to make that structured data. So one thing is that it will be sparse because some of the processes, some of the synthesis method is very simple and some is very complex. The table format is not suitable for material not always suitable for material science. So we needed some like more generative model. So to do that, the scope of the material science LM that we design is we include experimental information and also so including the material information, material structure, and properties. So material information is the is like a ID of the material, so including the formula, name, abbreviations, descriptions, processing method, defects, modification morphologies, structure and phase, crystalline structure, symmetry, phase, and so on. And also the properties is the Y value that we want to predict, and the structure is the for example, like what the material like in the physics, like that in the physics space, like what this looks like. And all this material, so one material like as I said before, material now is very complex. So one device, for example, one chip, like consists of multi-layer of the material. So we also, but the industry one is the device performance. So we also need to combine all the material structure into a device. So with that, so we create a world first material science large language model we call Darwin. So Darwin is based on the Lacuna de Llama, so 7 billion. So it's been published at last year, and we now have Darwin new one. So will be announced soon. How do we do that is we first have we call scientific QA generation. We have a lot of paper generate a lot of question and answer, and we train a large language model of large language model like Llama to fine tune the model to become to make a material science large language model. Yeah, so that is our model training method. And so firstly, I want to introduce more about scientific QAG. I think that will be also helpful for you guys. So scientific QAG, so it's a framework that automatically generation of the scientific question and answering. So it could include QA generator, state QA, QA evaluator, and state grading. So including 4 parts, and it's very flexible on the model. So you could choose for example, commercial large language model like GPT-4 or like Claude 3 or any open source large language model like Llama or like Mixtra, like from Europe. So it's very flexible. The data set that we did is most of physical science, but this framework is suitable for all field, so general field, so like climate, like energy, like even in social science, it also makes sense that one. But we are more focused on physical science, so we conclude 24 categories, over 4,000 papers in each categories, and 10 QA each pair for each paper. So we accumulate around 960 100 QA pairs. And we also have very detailed evaluation. So because the large language generated QA, so maybe some people will say that whether it's is correct, whether it's truly it's true the facts, whether we can use that for benchmarking other large language models. So we introduced the new metrics to secure that our automatic generated QA is very high qualities. Also, the reason why I forgot to mention one more thing. So the reason why we do that is because scientific field lack of open-ended QA. So for example, there are a lot of data set is the multi-choice. So for example, I have a question and A, B, C, D. What you should select? So there are a lot of QA data set in AI field is looked at that. But that one is not suitable for generative AI. So for example, GPT, like this large language training, because when you play with GPT, I think you all get to play with that. the GPT will not give you A, B, C, D answer. So you don't need to ask question like that, right? So you just like, what is the weather looks like today? And for example, like what is the material that I want to discover? It's open-ended questions, but with lack of that. So because generate that QA data set use manually is very costly. So GPT can use like people from Indonesia, Philippines, India, Africa people to generate a general QA. Human generate a lot of QA, but if for the science field you need a PhD, you need a professor to do that. So it's highly expensive. So we need automatic way to generate open-ended QA for training or benchmarking. Okay, I go ahead. So the method, so we have CDQA, so generate GPT-4. So when we generate CDQA, so it's like we have a paper. So we have a paper and we have a prompt. So you task it to formulate 10 QA pairs from the paper. It's that's like reading the paper. So for the generation of the QA, you just only to show the power of the model reading paper and extract the information from the paper. And that performance, that ability of the GPT model and also Claude and also large language model is very powerful now. So even the model maybe cannot understand what is aluminum oxide, what is the TNT, but if you just actually help to generate a question and answering, the model don't need to understand that actually. So it's just more like a semantic task. And now GPT is very powerful. It's very close to human. So we prompt design, including keywords, extract detailed information, and avoid depending on original paper because we need to generate keyword data set, which can use training or like can use for benchmarking other models. So we are avoid depending. So we avoid the generated questions and answer. For example, what is the figure one looks like talking about, right? So if we ask someone that question, you will say me I'm crazy because I don't know what figure one you mentioned. So we avoid that kind of question. And also QA generator, which is fine-tuned by Kuna and at QA evaluators, we use GPT-4 to evaluate that. So we design a new metrics for that for QA task in NLP. So we call RACA, so relevance, algorithm, completeness, accuracy, and rhythmness. So RA is for Q and CAR is for A. So R is Q relevance, so how relevant the question to the source paper, and algorithm, the degree of the context dependency, must not refer to demonstrative content from the original text, like figures or tables, as I mentioned before. Completeness, so whether the answer covers more relevant expected questions, and whether answer effectively utilize the details in the papers. And accuracy, so how well the generated answer correspond to the relevant facts in the paper. So reasonableness is whether the answer is logically coherent without contradiction. So this is our metrics. For example, like previously in the NLP, that is there are some very simple metrics, only like some statistical metrics like blue, like it's very simple and which is not suitable for that task actually. Okay, so with that, so this is our metrics, and we use that to filter our general QA, and then we create Darwin. So Darwin is so we call instruction fine-tuned large language model. So for material science, so we show two very good abilities. The first thing is very powerful in material design. So first is it's better than dedicated machine learning model now. So for example, like in the organic soil PCE predictions, so supervised the machine learning model, so brand NLP, the accuracy, the MAE is about 0.5, 0.4, and our model now is more accurate than machine learning supervised designed machine learning model. And generative and also powerful than other supervised fine-tuned generative AI model, including Llama and GPT-3. And it is a generative model, so you don't need to design, as I mentioned before, like machine learning, you need to design new descriptors, design new models anymore, just a simple prompts. So what is a PCE, so power conversion efficiency of that molecule with the organic soil cell? Just that very simple prompts, and you can get the answer. So so it works in both in organics and also the training data set used. So the training data point, number of the training data point compared to machine learning is much less. So for example, like we train the machine learning model, we maybe need 800 data points to train the model, and now with genetic with large language model. So we do supervised fine tuning. We only need less than 100. So you can regard a large language model is alright. So machine learning model is a blank. So it's a baby, like just born, and it don't know anything. It's a blank. But for large language model, like it's already like a PhD or like a master level, and you just need a little bit data to fine tune to tell them like what I want to do, and it can learn a lot. It can learn very fast. Okay, so this is first thing, and the rest thing is that we have better zero shot answering than GPT-4. So not in all cases, only in science, so only in material science. So for example, like we can answer more details, like more people interested in the like information. For example, like how does the pore structure of cobalt or sulfur oxide and silicon oxide catalyst compare to that other cobalt catalyst? And how might this influence its performance in single wall carbon nanotube synthesis? So it says that it is a high percentage of the metal pores and with the average diameter 50 nanometers. And the GPT answer is a pore structure can influence the distribution size, except of active site, or unique pore structure might lead to improve the dispersion of the copper particles. So because I already asked you, how does the pore structure affect that, right? So pore structure definitely can because I asked you. So GPT is kind of like a repeat my questions. So it looks very scientific, but it's nothing. So it didn't have any useful information. So the truth is that the pore size is around 32 nanometers with a surface area about how much, and which fails the dispersion and stabilization of the cobalt particles, and therefore influence the carrier selectivity and the yield of single wall carbon nanotube. So that is something like our model improved. So we provide more scientific details in the answer. So this is more brief comparison, so including physics, chemistry, material science, and others. So in the prediction of physical properties, molecular design, so also NLP task, and also multi-choice questions. So there are some application scenario of the LLM, so in material discovery. So first thing is that we can extract information. So as I mentioned before, it's super powerful now with the GPT model and also our model, not our model. So our model is open source, GPT is closed source. So if you care about data privacy, yeah, use our model. Yeah. So previous so you need a 50 scientists, 50 scientists to do series to build a database. For example, for purpose castle cell with data principles. But now you only need the large language model. So the each paper you just need less than $1, and 1 second you can generate a data set, like the human like these professors postdoc people do. So LM can process like complex 10-page scientific documents in 1 second, while a switcher needs 20 to 30 minutes for 1 page. So it's very super powerful for generate data set, especially from the text. It could be literature, it could be patent, it could be report. This is the data set that we create. So over 50K device data set, over 100 parameters, 1 second process 1 papers. So use GALI, yeah, so use our Australian supercomputer. So this is the per-schedule cell dataset parameters. So including stack information, cell information, methods, specificity. So there are a lot of sub relationship. So it's very complex, but that's all can be done by a large language model now. So also we are working on other field, like for example, we just published a Nature scientific data paper on self-cleaning materials. And also we are carbon nanotube, LED, quantum dot, these materials. We are working on the data set generated by large language model. Another one is like so you can leverage large language model to predict new material. So yeah, so we create a world record in experimental material design. So it's by Lawrence. It's verified by Lawrence Berkeley National Lab in US. The material project is our most famous open source material benchmark. So bench. So now our model are the world most accurate model to predict the experimental bad guy. And also device design. So can automate the formulation of the perovskite cell production. So for example, I ask a question, design the perovskite cell with how much power conversion efficiency and under what situation. So it give you a very detailed recipe to synthesize that solar cell. So including like a substrate stack sequence, ETL statistics. So it's here that, yeah, so here like each stack, so there are 5 layers. So I will tell the model will tell you each layer you use what material. Yeah, the inference. So each layer use what materials and also like use what solvent, even use what method to synthesis, and also the temperature and also and the time to do that. So it's very detailed recipe. Now also can generate a large language model now. So this is another thing that we are another application scenario that we are doing now. So we want to so because in literature, like or natural language are mostly empirical descript knowledge. So we are want to also give more like physical limitation of the model. So for like because language is very freedom, right? So we want to create a universal embedding for material discovery. So this embedding is combination of the sentence of the literature in the empirical knowledge and also the structural knowledge, like this material structure. So material structure, like we do calculation, so we do like that. It's a 3D structure, XYZ, and also their angle. So for example, this is each atoms and their the XYZ coordinations, and also like their like force, like kind of like that things. And want to combine these both information to convert a new embedding for material discoveries. And this research, like we are still ongoing, and the performance is pretty good actually. So we are doing the scaling now. So you could see the with the DFT, so with the traditional like physical calculation, like it's about 31% of the accuracy. And with word embedding, it's pretty low, only 8%. And with sentence embedding, so we increase the more information. So we 47%. So we embedding all these sentences compared to word embedding is only embedding the chemical compound name of the material. So we improve a lot with the sentence embedding. And we are combined after we combine the sentence and the structure embedding, we increase to 54 percentage, and we're still increasing. Also, this model can be because we use a lot of contrast learning, so this model can be scaling. So we can make the model learn a lot of infinite like different material structures and create a more powerful embeddings and with more parameters. So this is a very I'm so excited about that actually. So yeah, once we have more result, I will show on my on my on my social media. Yeah. So the new parallelism. So we want to achieve like a LLM driven like a self-driving material discovery. So and scientific. So my vision in the future is a material lab like maybe like your house, like that large. Only the one scientist. That scientist is a material scientist. We don't need any. We don't need too many like material engineer, like engineer to do the like to help you to do experiment like that. All things automatically. So scientists ask questions, have the idea, and the model will like give you like a basic experiment design, and you could refine that, and you could like you play with ChatGPT, like you could refine the experiment design plan, and then you send to the you could do simulation like to help you screen out like which material like you are not it's not reasonable, and screen out some candidates, and then the large language model also can use agent to help you to execute the experiment and then feedback to the model, and then it's an iteration. So it will iterate until you find a new recipes that saturate your needs. So that is my vision in the future. So fully automated, autonomous material lab, yeah, with large language model. So with that vision, so we need to do a lot of agent because large language model cannot do experiment, right? So cannot do mathematical calculation. So need an agent to do that. So this is our basic framework. So the large language model, we give the mechanical constraints. So the constraints can be encode specific experimental conditions, predict hypotheses, interactions, associations, and then model simulations and the simulation result, and then compare with the data set. So we have a big data set, and the simulation result will well, by translating this simulation result to text, we provide new simulation supervised data that could improve the large language model. And then we do the iteration again. So until we find the material that we want to achieve our mechanism constraints. Yeah. So that is very similar to human. Like actually, I do experiment. I'm doing like that. So every day I do experiment and I find that how close my material performance close to the target. And I think large language model can replace me in the future. So this is the simulation scenario that I'm doing. So we are doing like a use agent to do to control the very complex like some atomic or molecular simulation software like LLMs and Raspberry. They are very famous. And so this is the workflow of the deepest energy simulation. So for example, input and there are some optional things, and all these things can like use a large language model to do that. And then the agent, this is the example that I test on Getty. So for example, like do structuralization of the genomic oxide using the software and the water mechanic algorithm that you want to use, and then it fully automatically execute that one and submit the task on the supercomputer and give me the result. So fully automatically. So this work previously you need to train the PhD for 1 year maybe, but now 1 week, maybe less than 1 week. Yeah, so you can you can have people to help you to do the calculation. So that is super efficiency improvement. Yeah. And also self-driving scientific discovery, like with large language models. So as I mentioned before, we also have tests so this is the University of Toronto example. So this is the recipes that human written, and with a large language model, it can transfer the language, structured language that could be understood by the robotics, and then it will execute the experiment. Summary. So yeah, we'll keep improving the Darwin. So the Darwin is not a generative model that compete with GPT-4 or Claude 3. So we are only focused on material science and chemistry, and we want to integrate with the other large language models and we want to apply the large language model deeply into the material discoveries, and this is the play scenario, so including text-based work, liberate the productivities, and find new materials. Thank you.